Good afternoon, welcome everybody to today's COSI seminar. We have Dr. Philip Gatt from Lockheed Martin Coherent Technologies. Dr. Gatt received his degrees in electrical engineering from the University of Central Florida. He then worked as a research scientist at CREOL, the Center for Research and Education in Electro-Optics and Lasers there in Orlando. He was the principal investigator in the laser radar program there. And then he moved here to Colorado to Lockheed Martin. And there he's now a technical fellow, which is one of the alternatives for technical people there, either technical fellow or manager. So the technical fellow way.
It's much more fun.
And it has over 80 publications in optical remote sensing field, and it's co-author of a chapter on wind LiDAR, and was recently published as part of the book of laser remote sensing. So, welcome.
Okay. I think you have a staff member that also wrote a chapter in that book. I can't remember her name.
Oh.
It was a chapter. We were asked to write a 30-page chapter to go in a book. It turned out being 300 and some pages. But we got it right. So Sammy Henderson and Milton Huffaker and myself wrote this wind LiDAR chapter. If you have a chance to read it, and if you're interested in wind sensing with lasers, it's a good read. So my name is Phil Gatt. Thanks for the introduction. I'm double E. How many are double E? Yay. How many are physics? Perfect. And applied math? Okay. Did I leave anybody out? Okay. Okay. Great. Most of the people I work with are in that group. Double E's and physicists, applied mathematicians, and people in with optical backgrounds as well. So sort of the history was I was a 5-year postdoc at CREOL studying laser radar and was getting my own funding and built a lab and trained students and did some really cool stuff. But there wasn't that much funding available back in the early 90s, and Coherent Technologies in Boulder, Colorado was a company of 34 people that specialized in the exact same thing I was interested in, coherent laser radar. So that's why I came here to work for them. It was really cool. There was 19 PhDs out of about 35 total staff, which made it for a really fun, exciting environment. And it was just the opposite. I'll explain. I'll say it here in front of you guys because you'll get a kick out of it. It was just the opposite of CREOL. CREOL was a research institute with, at that time, about 20 faculty, and I want to be careful. If I go too far, stop me. The problem with CREOL for me, anyway, was there was competition among the different faculty members. You competed for the students, you competed for NSF funding, you competed for everything. You competed for lab space, you competed for everything. And so it was like dog eat dog. It was not a fun environment at all for a guy like me who was just up and coming and didn't have the, I wasn't a 10-year faculty, I was a research associate, and I had a lot of money coming to me from the government. There was a lot of jealousy and infighting, and so I didn't like it. When I came to CTI, it was a small company and everybody working towards one goal, and it was a lot of fun. And it was these 19 PhDs all trying to do the same thing, and so it was a totally different environment. So I'm still here. So that company grew from 30 people to about 250 over about 10 years, and then 4 years ago we were bought by Lockheed Martin. So now we're a part of 150,000. But we're still sort of autonomous. So we're in a couple of buildings. We call them 1 and 2, and we're in Louisville in the Colorado Tech Center, just off of Highway 42, or I'm not sure what you want to call it, but Dillon Road. We're between Dillon and Highway 42, just east of 287. It's an old picture, but probably a lot of the people are still here. This was our old building in Lafayette. but that building, we're no longer in that building. 290 people now, 35% masters and PhDs, lots of lab space. What do we do? This chart talks a little bit about what we do. We do a lot of modeling and phenomenology. I'm the team lead for the modeling group, which consists of about 8 scientists. Tomas is one of the people on my team, in my team. One of our biggest claims to fame, if you will, over the years has been our expertise in laser development. We pioneered, not me, I'm not a laser jock at all, but in the R&D department you'll find that it's like you're either a laser jock or you're something else. I don't know. That something else is you're a receiver guy, you're a modeling guy, you're an imaging guy, or you're a laser jock. So CTI pioneered the thulium, holmium, YAG lasers. I don't know, you guys probably correct me. I'm not the laser, I don't know much about it, but 2-micron laser development at CTI was very strong in the 90s, late 80s, all through the 90s. 2 microns, I'll explain to the people, was advantageous because it's eye safe and solid state, has a good it's a good wavelength for scattering off of aerosols for doing wind LiDAR. Longer wave has less target cross section, so it's harder to get echoes back. So we do transmitters, we do receivers, we do algorithms, we build entire systems. Then we were bought by Lockheed, and now we're part of Space Systems, and so now our focus is putting systems in space. So it's changed a little bit. This chart sort of talks to a lot of the different business areas. Well, of course, we work with the other lines of business of Lockheed as well, like IS and GS are into biometrics. That's one of their business areas. So 3D face imaging is important. And I don't need to walk you through all these examples, but you can kind of just look at it. I would say this is probably not the only areas that we play in, but and these charts are probably more for customers as opposed to you guys. I could probably put in some other things that would be more exciting to you. CTI's, of course, claim to fame is that we have the world's best scientists who are the most knowledgeable with respect to coherent laser radar. That's our expertise. That's what we do really, really well. And many people believe that you couldn't put a coherent radar on, say, like a helicopter because it vibrates too much, or you can't put one in space because they're too tricky, they're too sensitive to misalignments. Well, we've solved many of those engineering problems. We've built robust systems that fly on aircraft and helicopters. We've taken them all over the world, done all kinds of really cool things with them. Which I'm not really here to talk about that. So the talk today, of course, I want to introduce you to who we are. We'd like to get some of the smartest in this group to come work for us. So send me your resume when you get close to graduating. That's part of why I'm here. So this talk is going to be, I call it Unconventional Imaging Developments at Lockheed Martin Coherent Technologies. And I'm basically going to talk about 3 different imaging technologies that we've worked on over the years. The one I left out is synthetic aperture LiDAR. So we do both inverse and forward synthetic aperture radar at laser wavelengths. It's another one that I didn't talk about or have much. I don't have anything in this packet on that. Feel free to contact me, and I'll get you in touch with Joe Buck. That's the place. That's his specialty area. So this talk, I'm going to talk about 3 different imaging technologies. All 3 of them are 3D, 2 and 3D. The first 2 are coherent detection. The third one is what I would call a direct detection analog to the second one. And you'll see what I mean. And I would maintain that anything anybody does in coherent detection, somebody else somewhere along the way has found out a clever way to do it in direct detection. The key difference is that the carrier frequency is not the same, or put another way, they use a synthetic wavelength. Like maybe they modulate the power of a laser with a sine wave at say 300 megahertz, so they have a 1 meter wavelength. Whereas when we transmit a you know, 1 micron laser and do coherent detection, we have a 1 micron wavelength. So the Doppler shift is 2V over lambda, and lambda is 1 micron for us. But you can do Doppler direct detection with a synthetic wavelength, but your lambda is much, much bigger. So anyway, so this third technique called, I call it 3D fringe imaging. You probably know it as Fourier transform profilometry. It's a direct counterpart to the second one, which I call spatial heterodyne because I'm a double E. You might call it digital holography because you're imaging people. I don't know. They're basically the same thing. So the first thing I want to talk about is one that I pioneered. Myself, Brian Krause, and Bruce Tiemann worked on a project. It was an SBIR, one of those get 75K to do a study, and then you can, if you do a really, really good job, then you might be able to pull another $750,000 out of the government to build something and demo it. And that's what we did. And, well, as you probably know, does coherent detection, do most people understand coherent detection where you mix a reference laser with an echo or with another laser, just like holography, except I guess generally in holography you use the same wavelength. In LiDAR we tend to have, it's like a interferometer. One leg is extremely long to the target and back, and the other leg is extremely close. It's just your, to your receiver. And so just think of a long arm interferometer, and we tend to use some device to give you single sideband frequency modulation, like an acousto-optic modulator, so we can shift the frequency so that our zero Doppler frequency is not at DC, it's actually somewhere away from DC, so we can sense positive and negative shifts, and we don't have to deal with DC problems with DC interference, so on and so forth. Those technologies tend to require very high bandwidth detectors and electronics and so on and so forth behind them. Why? Well, if you want to get range resolution on the order of an inch, or sorry, a centimeter, you need how much bandwidth? 1 centimeter needs how much bandwidth? 15 is the answer, and tens of gigahertz is close enough for me. So C over 2B is the first order thing. If I want a centimeter, I need 15 gigahertz, so C over 2B is a centimeter. 15 gigahertz is not easy to get in a photodiode. Well, telecom devices, yeah, but not necessarily. And then behind the photodiode and the amplifier and preamp the amplifier and the digitizer, blah, 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 it's kind of hard to do. And what if you wanted a tenth of that? A millimeter. Now you're talking 150 gigahertz. It's kind of hard to do. So, and suppose you wanted to do that in a staring array. So imagine you built this, you managed to build the 15 gigahertz receiver that gave you the 1 centimeter resolution, and now you want to create an image. Well, what's been done in the past was people would just raster scan a single element detector to form a 3D image. So this concept here gets around most of those problems, gets around the raster scanning and gets around the bandwidth issue by doing what? By optically demodulating a wide bandwidth. That's the way I look at it anyway. You transmit a very wide bandwidth waveform, you demodulate it optically, and what you end up with is signals that are low bandwidth for targets at over a small range interval. That's the notion of this linear FMCW. It's not, this technique, this optical demodulation only works because we're transmitting a linear frequency ramp. You do a parabolic ramp or something else, it doesn't work. So here's the notion. The idea is that you transmit a waveform CW and you sweep the frequency from F1 to F2 in a highly linear fashion. If you manage to accomplish that, and if you transmit that to a target, you'll get an echo back which will be delayed in time by some target delay time. And what you see then is over this entire ramp time, well, not the whole thing, but over a fraction of the ramp time, and actually this is really grossly off. I mean, it'd be like for typical targets, the distance here, speed of light is so fast. The ramps are long, they're millisecond class ramps. And speed of light, a millisecond is what, 150 kilometers. So we talk about, targets 10 meters away. So these things are right on top of each other. But the key is that there's a fixed difference frequency. So I'll get a sine wave out of this guy that's proportional to how far away the target is. Does that make sense? So all I have to do is take my signal, compute an FFT, and I'll get something that gives me information about how far a target is, depending on what frequency it lights up. And that's pretty much it. So you have a single frequency laser that you can chirp. Oh, and I didn't mention the other part. The other part is now you can do this with a camera. Why? Let's say I put in 15 gigahertz of bandwidth. But let's say my target is so close that this IF frequency never exceeds 50 hertz, 100 hertz, a couple hundred hertz. You can now start thinking about using low bandwidth electronics like a camera whose frame rate satisfies Nyquist for the targets that you're looking at. That's the sort of novel idea. So we get rid of the scanner. We don't have to do any stitching. We still get many, many gigahertz or terahertz of bandwidth optically. We demodulate optically, and then use a low bandwidth device. So what do we lose? I mean, you never get anything for free in this life. Of course, I'm wrong. Now, somebody will get me wrong, but my experience is almost always if you gain something somewhere, you lose it somewhere else. So the advantage here was we got rid of the scanner, we got rid of the high bandwidth electronics. What did we pay for that? What did it cost? Well, no, but yeah, and we'd like to use faster cameras. The answer that I'm looking for is you can only see targets over a finite band. Once the target gets far enough away, the IF frequency gets too high and you're out of the bandwidth of your camera. Had you built the wide bandwidth, 20 gigahertz receiver, you could look at targets at all ranges simultaneously. So you always, whenever any of the things I'm about to show you, they're like workarounds for the hard way to do it, which has the full bandwidth. They're workarounds to get around those full bandwidth requirements to still give you something really, really cool. But I always look at it and say, I always ask the questions, well, what did it cost? What did I lose? And you'll always find there's something usually when you come up with a way to get rid of bandwidth. So I don't need to go. I don't have very, very few equations here, although I'm the equation jock. So I teach a short course on laser radar, and if you took a look at it, you'd see, okay, this guy does do theory. So this was one of the coolest pictures we got out of this device that we built. It used a 540 by 612 Sensors Unlimited infrared in-gas camera that has a variable region of interest, so you can crank the frame rate up from the slow at this rate. I don't remember at this size if it was 30 hertz or 50 hertz or whatever, but if you neck it down to like 100 by 100, you can maybe get kilohertz out of it, and you can get up to like 10 kilohertz out of this camera if you get small enough regions of interest. The ramp was a frequency ramp of 2.25 seconds roughly, and 41 gigahertz of chirp put on there, which gives you, as indicated there, about 4 millimeters of range resolution. And I didn't give you the equation, but generally speaking, your range precision can be better than your resolution by just throwing more photons on it or averaging or doing something. So we were estimating about 1 millimeter precision. This tank, this Humvee, of course, it's a model, and those are 1-inch holes here. So you get the size, you get a feel for the scale of this thing. And I'm probably not impressing anybody because I'm sure you've done stuff like this here too. But these little, the divots on these tires are tiny, and we're just picking up all kinds of really fine scale stuff. It's not quite flash. It took us 2.5 seconds. So it's not quite flash, but there was no scanning. Pretty cool stuff still. What's the Achilles heel in this technology? That's one of them, but that we actually overcame it, as you can see. And he's got a good point. I don't know how much time I have, and I don't want to go too slow. But he's got a good point. If you don't transmit a perfect linear function, if it had a quadratic component or some noise on it, then your IF frequency is going to wax and wane, right? And you're going to broaden your spectrum, and you aren't going to get that good range resolution. you're going to broaden the spectrum of the sine wave. So yeah, you want a really, really linear ramp. You'll find out that...
Do you guys actually work hard at getting a linear ramp, or you do something else?
No, yeah, my invention came up with a design that's not patented, but it's sort of a trade secret. It's an active closed-loop servo, essentially. And that's all I can really say. The Achilles heel I was thinking of is something else.
Yes, hold still for 2.4 seconds.
There you go. That's it. Doppler will kill you, right? This was a long ramp, so you don't need a very powerful laser, you know, because you're integrating how many photons are in a 1-watt laser in 1 second? First order? 10 to the 19th-ish, right? So there's tons of photons in a lot of time with just a low-power device. So we went for 2.5 seconds, which is a long time, and if there was any motion during that ramp time, it would blur the image. We would take that sine wave and put it right outside the detector of the camera bandwidth, the frame rate. So we came up with a method for dealing with that, which I won't get into here. But it cost us in SNR. Nevertheless, this was this is of course just one frame that I'm just rolling it around and showing it to you from different aspects. Range is colored, coded, away from the lidar. So this is one of my favorite images that I've seen us develop, because of course it was my idea too. So I did the phase 1 SBI. That's the kind of way I work. I like to get things off and running, you know, and do a proof of concept, demonstrate to the world that it's feasible, try to get the money in to go to the next step. But then when it gets time to build something, it's not as exciting to me. I mean, after they build it and they go through all the pain there and they're out in the field collecting data, and that's where I get back involved again. So it's my idea. I come up with, I prove it works. Somebody else will build it for me, and then I go play with it. That's what I like to do. Because building it can be painful. I mean, you know, you got to deal with procurement, and it just goes on and on. Same thing, but by the way, because there's a camera involved, you can get a passive image, and you can do data fusion and overlay the passive image on the 3D data, and that's what you're looking at here. So the tires look black, and so on and so forth. That's pretty cool. That's all I have on that one. Now I'm going to talk about the digital holography. Joe Marin is the pioneer behind this. Rick Kendricks is also involved. He's from another branch of Lockheed in California, in Palo Alto. The rest of these folks, Nathan Seldrum-Ridge, Taylor Groh, Andrew Maum, myself, Carl Embry, Robert Nichols, and I think even Tomas was involved at one point. Probably should have had your name on. I got your name on the other one, by the way. These are people that have been working on some hardware demonstrations and done some really cool stuff. Did I go the wrong way? Again, because I'm a double E and I was brought up through radar and LiDAR, sort of the wide bandwidth single channel receiver, I tend to try to cast everything in that against that backdrop. So you may call it digital holography, I call it spatial heterodyning. Bottom line is what you do is you're trying to spatially modulate the field on your focal plane so that you can get access to the amplitude and phase of the field. All you would need to do that is mix it with a local oscillator, but to separate it from the DC components, just like we do in, like I said earlier, in our wind LiDAR or any of our other high bandwidth LiDARs, our zero Doppler is offset. We use an acousto-optic modulator to offset it away from DC. They do the same thing here. You put in the fringe pattern, and that allows you to offset your image information away from DC. And you just grab a single sideband like you might do in the temporal version, and now you can end up with a complex data from a device that only measures power. What I'm going to talk about mostly today is an image plane version of this technology, but you could also imagine you could do it in the pupil plane. In fact, that's where Joe Marin initially did most of his work, was in the pupil plane. The advantage of doing it in the image plane is you can simultaneously get passive images as well and apply the atmospheric correction that you did, say, from the coherent or the laser data, and apply that No, you can't. Never mind. Forget. Said that wrong. Strike that. The beauty is being able to simultaneously get active and passive data. What else is on here? Coherent detection, that means what? It means lots of things. One thing it means is that your sensitivity is about 1 photoelectron, which is pretty good. It's not a Geiger mode device, so you don't really see a blip when a photon comes in, but the noise level is about 1 photoelectron. So it's highly sensitive, especially in the infrared where there are very few nice wide bandwidth detector devices that have a lot of gain. So we use the reference laser to give us the gain, is essentially the bottom line. The other thing that's really cool about this is you can do atmospheric compensation with autofocus algorithms, and you can use multiple wavelengths or some other way to get what? To get bandwidth, because bandwidth gives you range resolution. So if you did it at a couple of wavelengths, you can start talking 3D. So rather than reading it, I'll just sort of walk you through it. So there's a CW reference laser involved. We carve out a pulse. We don't have to, but we do. And that serves as our what I call local oscillator, or what holography people would call a reference beam. This reference beam looks like a point source in the pupil. And then you also take some of this CW source and amplify it, send it out to a target. This is also pulsed. And light scattering from the target comes back into the receiver and mixes where? It mixes here, not here. A lot of people think of it as mixing here. The fields mix where they're added. Maybe mixing is the wrong term. They're added here. And then the camera or the detector is, of course, a power law sensor. Sorry, a power sensor, so it senses the magnitude square of the electric field, and that process is what converts an addition into a multiplication, if you will. So it's maybe both of this, all of this is like the mixer. The key here is that the local oscillator looks like a point source in the pupil, and that both of these things are pulsed. This is what makes this advent get around what I said was the Achilles heel on the previous one, the FMCW. So I can make this pulse as short as I want, and the shorter I make it, the more Doppler or the more motion I can handle. Why? It freezes the motion is one simple way to think of it. Or to think of it another way, if this was a millisecond, then I could handle up to a kilohertz in Doppler. 1 kilohertz in 1 millisecond would give me 1 sine wave. That would be a null, and I'd get no signal. So, and a kilohertz of Doppler isn't much. It's, what is that, a micron per second at a 2 micron wavelength. So it's not much motion. So maybe I want to deal with meter per second kind of motion, which is megahertz class. What that means that this needs to be microsecond class or smaller. But we're talking about doing something in, say, the tens or hundreds of nanoseconds for these pulses. That freezes the Doppler, it gets around the Doppler problem I described, creates other problems that I can get into, but I probably won't. Timing overlap, for example. These things have to land on this detector at the same time to get good efficiency. So you've got to time this guy, so on and so forth. But it does, we've demonstrated with moving targets, it works really, really well. So what is the concept? I think because you guys are all in the computational imaging and sensing department, you've probably all have seen this sort of thing. Essentially, there's a power or a photocurrent that's proportional. There's 2 beams involved here. There's a reference or a local oscillator beam, and there's the beam coming back or the photons coming back from the target. So they both give me a DC contribution, if you will, and then there's a beating between them. Again, this is you add 2 fields and then you detect it with a square law device, and you get all these terms. And you can't really see it. This is not one of the best ones, but the reason for doing it is it kind of is, well, we didn't want to show you stuff we can't show you. So what is this? I asked Joe Marin what it was, and what it really is a target about that big. It's in the lab. It's about that big. It really is tiny, and It was just one of the demonstration experiments. You can't see them here, but there are 45-degree fringes. I think they go that way, not that way. I'm not maybe one of you guys can tell me if I have it backwards based on this. But essentially, you've set it up so that the reference beam and the incoming field are at an angle such that you get a fringe pattern across your camera. That fringe pattern essentially is doing a modulation. There's a spatial frequency associated with that fringe pattern. And so these terms, the DC term from the reference beam is actually a really, really, really bright spot right at DC. And then there's this term here, which is when you go into this space, is an autocorrelation function of the image, if that makes sense. Because this is the Fourier space from the image space. So, and then these terms are essentially the signal modulated out to a different spatial frequency. So this is your image spectrum, the signal image spectrum away from DC. And as you probably know, if you don't take both sidebands, but you just take one sideband of your single sideband demodulation, essentially what was a real signal comes back as a complex signal. You have access to both amplitude and phase. Whereas if it was like here, it's still a real signal, so it's like a sine wave that you have to get amplitude. So that's the trick. So you beat these two lasers together at an angle, set up fringes. The secret sauce I won't go into in terms of how you set those up and what the spacing is and so on and so forth. You set them up, Fourier transform, you acquire your single sideband. Throw away the rest. Now you have this. Do a inverse Fourier transform and you get a complex data set whose magnitude squared is this image. It's a coherent image, it's speckled. I don't see enough speckle in there, so I wonder if Joe did some averaging. He might have. So this was the passive image, this is the active image. Again, sensitivity of 1 photoelectron per pixel. Even though this camera might have readout noise of thousands of electrons per pixel, because we've got a local oscillator on there, that we basically put millions of LO photons in that same well, or whatever it can handle, hundreds of thousands. And that makes it so that we dominate all the LO noise is the dominant noise, and because of this, the LO actually amplifies the signal field also. And that's what makes us really sensitive. The LO amplifies the signal, and it becomes the dominant noise. And at the end of the day, you get quantum limited detection, regardless of how noisy your receiver is, electronics. I'm being a little loose here, but that's the idea.
What about the contrast? The contrast in the image, does it increase?
Pardon me?
The contrast in the image, is it...
Oh, the contrast, yes, absolutely. So you do lose DC contrast. The contrast on this piece here, if that was your image, would be poor because of this big giant pedestal. But this is the piece we're looking for.
Compared to basic imaging, do you have any gain of contrast doing all this coherent
No, I wouldn't think so.
resolution?
Huh?
How about resolution?
Spatial or temporal?
Spatial.
You can, no, I wouldn't say it has any, coherent detection doesn't have any better spatial resolution unless you're talking about things like synthetic aperture, LiDAR and radar. Have you ever, who's looked at synthetic aperture radar? Do you wonder why there's an extra factor of 2 in the angular resolution than what you're used to? Instead of land over D, it'll be like land over 2D. When you get into it and you compare it to just passive imaging versus this active approach, you find there's an extra factor of 2. Why? Does anybody have an idea why that is? Round trip is what one person proposed to me. I disagree. I maintain it's the angle of the doubling of the angle. It's like the disco ball, right? So you illuminate a disco ball, it's rotating at some rate, and there's spots that move around the room. How fast do they move? Twice the rate. And it's the same factor of 2 why the active synthetic aperture stuff has double the spatial resolution. Sorry, that was a side point that you asked the question. So. Usually, like in LADAR, there's always a 2 in there somewhere associated with the round trip. But this is a different 2, I think. So what else can you do? Well, what if you did it with 2 wavelengths? Acquire image at wavelength 1, acquire another image at wavelength 2. Now you have a difference in wavelengths, which means a difference in carrier frequencies. So there's some bandwidth now associated with this thing, the difference in the 2 carrier frequencies. And that's exactly what Joe did here. So he set up 2 lasers to be offset in frequency by gigahertz, collected 2 frames of data, one at wavelength 1, one at wavelength 2. Each one gives you a complex image, just like I described on the previous chart. But now, between these 2 complex images, you can start looking at the phase. And the phase is where range is encoded. And I don't have time to go into all of it. If you think about it, you'll understand it and it'll make sense to you. So if you basically extract the phase, however you like to do it, it's basically an inverse tangent. And you have 2 complex signals. So get the phase. This is a phase map. Now you can start to see what this guy is. It's a truck. Here's the cab. Here's the hood. There's the bed. Again, it's this little tiny toy I told you about. And there's sitting off to the side is this little tiny model of a human. And one of Joe Marin's points to me was that in the passive image, you cannot see this little human. And it's even hard to see in any of these active images, but in the 3D image, it really comes out. Now some of the cool stuff that's all pretty cool in itself, but then some of the other cool stuff about this technology is now that you have access to image field, amplitude and phase, not just the power, then you could start doing cool things, like you can go back to the pupil plane and you can put phase screens in there to try to compensate for distortions of the optics or the atmosphere, and then come back to the image plane and do things like that. And that's exactly what was done here. So this is an example. So this is the raw data. You can kind of see this Air Force bar chart in there. You zoomed in on this, you can see the fringes that were set up with the reference beam. Of course, we already talked about that, and you understand that. Well, window out, one of the sidebands. So this is really not much better than that yet, except it's now a complex version of this real data. And it doesn't have the big DC level from the local oscillator reference that kills the contrast you were talking about. That got filtered out. And then Joe Marin applies his secret sauce, which he calls image sharpness metric maximization. So he essentially defines a sharpness metric that looks something like summing over the intensity data, the magnitude squared of this complex image, summing it in some region, and summing it raised to some power p. P is part of the magic sauce. If p is greater than 1, I think you try to maximize this. Sam Thurman, his counterpart, he does a negative power, so he tries to minimize it. But at the end of the day, if something that's sharp should have something that is focused and crisp and sharp and a lot of detail should have a large value for this. And if it's blurry, when you think about it, you'll see it, that if something is kind of blurred or doesn't have if it doesn't have much contrast, then that number might be low. And it's basically it's just I don't know, I wouldn't call it a blind search, but it's a hill climbing kind of servo where you tweak Zernike parameters up to whatever order you pick. Joe generally does about 48 orders. And you tweak parameters while monitoring this, trying to maximize that guy. And it works. He's done a great job. So here was this data. It's a little blurry. Where did it come from? Did it come from the atmosphere, or did it come from the optical train? It's not clear. It doesn't matter. Except one is temporal and one is stationary. You Fourier transform to the pupil. You apply a set of Zernike phases. You measure the sharpness, you see if it went up or went down. You are in some sort of amoeba kind of hill climbing algorithms. What am I trying to say? Maximization kind of algorithm. There's a variety of them out there. And if you do a good job, you eventually get something that looks a lot more focused. So that was pretty cool. Joe talks about it in these papers here.
This only works for so-called isophonetic images.
Yes, very well. Very good. So that's the next chart. I'm glad you brought that up. Oh, no, that's the one after this one. So I guess this chart is just more examples of the same thing, but what's happening here is that, so the previous one was turbulence, not aberrations in the optical system, although it's probably both. What's happening is this is the most benign turbulent case at the bottom. Turbulence, atmospheric turbulence is usually quantified by this parameter called the index structure constant, Cn squared. Values in the 10 to the minus 15 and lower are kind of benign. Values at minus 13 and upper are really nasty. Boulders generally in that regime to minus 12. And then, of course, path length is important too. And I don't remember, does it say on here? 100-meter path. So this is a 100-meter path through very strong turbulence. 100-meter path through not so bad. So you can see the uncorrected image or uncompensated image is really bad here, and it's not so bad here. But after applying the autofocus algorithms that I mentioned earlier, this is what they come up with, and it's reasonable. They're a great improvement. And that's a huge improvement in my opinion. But there's also, improvement here as well. So now for anisoplaneticism, which I can never say. I struggle with it every time. So this chart, in this case, I'm not quite sure what was done to change the geometry, but it's such that the atmosphere now, that your field of view or your field of regard now encompasses many independent atmospheric paths, if you want to think of it that way. Or in angle space, the atmosphere is correlated over only a certain small angle. And so if you find a compensation, if you find a set of phase screens or Zernickes or whatever to compensate for the image, you can do it only locally well. You could do it globally, but it's just not so well, but if you try to do it locally, you'll be better. And so here was an example of where it was, this is the final corrected image when you use the full space. Tried to sharpen the full thing. It got that sharp. In the same data set, if you tried to sharpen just this region, it's sharper. Those two regions are sharper. But I'm not sure what I'd say about the rest of it. In general, this should be less sharp than that. And then if you just tried to sharpen one region that perhaps is within an isoplanatic patch or angle, you'll do pretty well at the expense of the rest of the image. So what it means if you want to do this wide field of view imaging over many isoplanatic angles is you have to apply this phase screen Zernicke correction over and over again for different isoplanatic patches in your image.
Right. Well, there are at least half a dozen competing techniques to do exactly the same thing. Not on more than any reference beams and stuff like that. The convolution, we heard about it, I think, last week. You have step interferometry, you have sharpness criteria. They all do the same thing, basically. So how does this compare to alternatives?
I don't know the answer to that. What I do know is that because it's generally more sensitive than most of the other systems because of the reference laser, that generally does better. And you get direct access to the image amplitude and phase. There's other approaches, like Joe's advisor, is that right? I don't think I have that right. They work together. Jim Feenup, does anybody know that name? Okay. So Jim and Joe worked together for years and years, and I managed to pull Joe away from Jim. It was kind of hard, and I got him here in Colorado. It took me 5 years to hire that guy. Jim Feenup does similar stuff without access to the field, amplitude, and phase. It starts out with the field, a direct detection, just a sort of passive image, and then you hypothesize phases, right? And you go through a phase algorithm, and it's very similar. It's just that this converges much faster and gives better results because you start out with the phase. Corrupted though it may be, at least you have a good initial phase. I don't know that I've answered your question, and you probably should hook up with Joe, and you guys could maybe talk about some of the good ideas for things to do next. So that's the end of my talk on digital holography and what's going on at CT. Oh wait, no it's not. Sorry. So some pictures. So there's a site called Table Mountain. You might know where it is. It's 5-10 miles north, where the radar antennas are. We're able to go out there and get access to like 2-kilometer paths where you're not going to worry about eye safety for civilians and things like that. There's Joe Marin with a wig. And that's the inside of the van. I couldn't show you all the pictures. Some of it was proprietary, but it's we didn't want to demonstrate the technology. We didn't want to embark on a laser design, so we used two of our wind tracer lasers. These are the devices. Some of you who were at at the cookie thing with me, heard me talk about our history. But so these are like 200 nanoseconds. 500 to 1 kilohertz, couple of millijoules. They're like 2-watt devices. 2 of them offset, so a lot of work was done to separate these guys by some fixed frequency, like 1 gigahertz. So we've got 2 lasers now transmitting with some kind of a frequency offset. Joe does all kinds of unconventional imaging, some of which I couldn't give you any details on, but if you can think of it, Joe's probably been working in. So distributed aperture, so on and so forth. So anyway, that was the hardware and a commercial I don't think that's actually the right one. There's another one you can't see, but the receiver is just a commercial off-the-shelf near-infrared or in-gas camera. Oh, so here's a lot of the parameters. Did I leave anything critical out? I don't think so. So 2 millijoules, 600 hertz, so 1.2 watts or something like that. 150, not 200 nanoseconds. I'm going the wrong way, sorry. So that's what the back of the van looked like. So we'd go out to targets anywhere from like 50 meters to a kilometer or so and do different experiments. This was a 100-meter data set. So there's the passive or close-up image. This is a passive image at 100 meters over the bandwidth of that in-gas camera. And this is the 2D spatial heterodyne image after turbulence correction. And then do it with 2 wavelengths, and you can get 3D, of course, as we already described. So now you've got phase. And then you can do whatever you want to that, like overlay. In this case, he's overlaid 2 things. He's overlaid the passive image, which shouldn't have speckle. And you can also just overlay the magnitude squared of your data. You can color code them in range or whatever. So anyway, so here's one that's just basically the laser reflectance overlay on a 3D shape, and the other one, I guess, again, is a passive one. All right, so that's is that going to stop? Yeah. That's the end of the discussion on this coherent detection technique that I call spatial heterodyning and others call digital holography. Again, as I think I mentioned early on, you can do a very similar thing without a coherent receiver, without a reference beam, without worrying about Doppler shifts at the same extent, because the wavelength here was a micron class, and now, essentially you could do different things. And in this particular case, what you do is you illuminate the object with a bunch of fringes. And so you get an image that has a fringe, has a sine wave multiplication, if you will. I'm going to skip past that. Just go straight. So you illuminate some object with a fringe pattern, and however you want to get that. And that creates, of course, an image like this. And this is what it's essentially a spatially modulated image. Spatial frequency modulated image. So everything we talked about before in terms of going to the Fourier space, being able to separate these things and all that's all possible here as well. Again, because it's not coherent detection, it might not have the sensitivity, so you might need a lot more laser power to go at range and things like that. And there's other, I don't want to get into all the details. I just wanted to, because this is something, this tends to be maybe cheaper to build, maybe not quite as capable, but doesn't have Doppler shift issues and other things. So just depending on the application, what you do, application tends to drive what's needed. But everything that I described before is exactly the same. So this was doing the same processing, go to the Fourier domain. I'll show you a picture in a minute. Carving out one of those sidebands to get a complex signal from a direct detection receiver. Doing some phase unwrapping to convert your phase data, wrapped phase into unwrapped phase, and then you map that to range. And you can actually map it to 3D coordinates. Then you can also take a passive image and you can overlay them. So this was, you were involved in this work, right, Brian? Tomas? And now I got your name, I think. Yes, second one. Okay. So this was the raw data. On the left, the active image. On the right, a passive image. Same guy. This is the spectra. In other words, this is the pupil. Well, not quite right. One of those quadrants is the pupil. And they're, setting up, you could probably see that the fringe spacing was kind of low. In other words, the modulation frequency wasn't high. You could see the fringes well separated. And then what does that mean? That means that, these sidebands aren't that far away from DC. If you used a higher spatial frequency, you'd push them out farther and get better separability. The other problem that's different between this and the coherent version is the coherent version, you had that really strong local oscillator laser, which was essentially a delta function in this space sitting right at DC. And that thing amplified your sidebands. And so that pulled these sidebands up really high compared to the autocorrelation of the Fourier transform of the image. So in the direct detection version, you get more interference is maybe one way to think of it, or this component here competes or disturbs that piece that you're looking for. So if you modulated faster, you could push them out and do different things. But this still works really, really well. So as I indicate, you carve out a section here, and that's now an asymmetric spectrum, which means in the image domain, it's a complex image, right? There was something else I wanted to say. Maybe I'll remember it in a little bit. This, I don't know. There's a lot of math behind it. And any of the direct detection versions of the coherent stuff, the math is a lot harder. There's a lot of nonlinear stuff that goes on, and like in this case, what is the range resolution? And it depends on not only the fringes, the angular spacing of the fringes, but how far away the target is. Like in coherent LiDAR, generally speaking, C over 2B gives you the range resolution, no matter how far away the target is. Here, the resolution depends on where the target is. So it's a little more complicated, but you can make things work well, and that's what's done here. So there's a wrapped phase image on the left and an unwrapped one on the right, and then you can overlay the passive image. Okay, I'm actually, I think, almost done. So that's really good timing. I have to stand back and look. So we, LMCT, besides all the other really, really cool stuff we do, we also do a lot of imaging. Very germane to this group here. It's all digital. We love the coherent stuff. And the direct detection stuff is cool too. But I always view that you can do more. I don't know. When you have direct access to the true amplitude and phase, you've got a more, what word do I want to use? Technically advanced system. I don't know. I think of direct detection as sort of the poor man's version of a LiDAR, if you will. That the high performance, high fidelity Porsche version is a coherent system as opposed to the Volkswagen direct detection version. Guess you can't say that about Volkswagen anymore, right? Because they swallowed up Porsche. So anyway, coherent 2 and 3D through different techniques. The one I didn't talk at all about was synthetic and inverse synthetic aperture LiDAR, not radar, which has its whole new set of issues that radar doesn't have to deal with. Of course, it has a whole set of issues. Radar has the same problem the other way around. They both have their own issues that each other doesn't have to deal with. Like we don't have to worry about main lobe sidebands and things like that because our lasers are so well confined. What I described earlier was all talked about in the image plane, but guess what? As I said earlier, you could do it in the pupil plane as well. You might see advantages in one over the other. Like a really, really bright object, a big glint might saturate your detector in an image plane version. But if you collected that data in the pupil plane, that glint looks like a plane wave, so it's distributed across all your pixels. Maybe it doesn't saturate, so on and so forth. Here you can get, in the pupil plane, you can get the passive image immediately, pretty easy, so on and so forth. So I don't know. We've done a lot of stuff outdoors. I haven't really shown you hardly anything of what we've done. I didn't have time and didn't know what I could show. I could only show you guys stuff that has been approved for public audiences. And the nice thing about coherent detection too, the spatial heterodyning, is it doesn't matter day, night. We are virtually immune unless we saturate the camera with the background photons. We're immune virtually to background light. Does anybody know what the noise equivalent temperature of a 1 micron coherent receiver is? Does anybody understand the question? How hot does an object have to be if I'm going to build a receiver that has a 1 micron reference beam? That's a coherent receiver. I'm going to take this thing and just point it at stuff. There's no transmitter, just this receiver. How hot does something have to be before I can see a signal above the noise or equal to the noise? What is the noise equivalent temperature? How hot does that black body have to be? You're getting close. Yeah. He beat you, but there's a great paper by Siegmann, the laser guy, the 1967 paper, Heterodyne something laser radar. It's a seminal paper that everybody who's interested in LiDAR and this kind of stuff should look at. And when you work out the details, because coherent detection is single frequency, single spatial mode, single temporal mode, single polarization, it filters out a tremendous amount of background light. Turns out at 1 micron that thing has to be 20,000 degrees Kelvin before the signal amplitude is equal to the RMS noise amplitude, or the powers are equal. That's a pretty hot source. So you take a 1 micron coherent receiver and point it at the sun, you won't see it. You'll burn up your optics, you'll burn up your detector from the DC term, but the beat note that you're looking for will be buried in the noise. All right? And by the way, we've taken our 2 micron wind LiDARs and passed them right through the sun. It doesn't bother us. You want to put some filtering to filter out a lot of that stuff so you don't burn up your optics, but it doesn't corrupt our heterodyne signal. So if I wanted to see the sun, I'd probably want to do it with a 10 micron receiver because at 10 microns the noise equivalent temperature is 1/10, and so it's like a 2K black body, and I can start to see them. That's the end of my talk.
We have time for one more question.
So
And I'll stick around. Anybody who wants to chat afterwards.
if you're looking at a target, say that's completely depolarizing, then, I mean, is that a problem for when you're doing coherent detection?
You can build, so coherent receivers, I always maintain, are, they're single, you need multiple channels for all the different pieces of information. So if I want to see both poles, I need a 2-channel receiver. If I want to see different spatial modes, I need more than one detector, so on and so forth. So yeah, generally speaking, if you don't do that, if you transmit, we generally would transmit right-hand circular, so it bounces off a target, comes back backwards, right? Go through the Stokes vector, I think is the right, is that the right one? Whatever. It's not Stokes. The pointing vector is reversed on the back pass. So when it gets into this quarter wave plate that caused circular going out, it actually flips it and makes it parallel, horizontal, linear polarization that's 90 degrees orthogonal to what was transmitted. So I didn't make that quite clear. Our passive switches are you transmit a linear polarization through a quarter wave plate, turn just right to make circular. I don't care, left hand, right hand. It goes out to the target, that reverses the pointing vector. When it comes back, it's the opposite hand circular, goes through that quarter wave plate and comes out 90 degrees from what went out. And so now you can use a polarizer to separate the echo from the transmit. I guess I didn't make this clear. Most of our systems are monostatic. We send and receive out of the same optics. And so we need a switch like that. A bistatic system, you transmit here and receive here, you don't need a switch like that. So because of that switch in our system, we don't sense both polarizations. Or even another way to think about it is a local oscillator is one polarization, and you're only going to interfere or beat against photons of the same polarization. So if you had 2 local oscillators, 2 channels, you can get all those photons.
Okay, let's do the last one.
Oh, I just had a question from some of the last image that you showed out at the mountain. The working distance was like 100 meters. I think we get quite a limited field of view. I was wondering what constrains your field of view to do that.
So as you might think about it, what's going to happen in the focal plane, or the image plane, is you're going to have a speckle pattern. You're going to have an image, you're going to have fringes on it, and it's going to be speckly. So if you want to size your speckle size to your detectors in a certain way so that you get good efficiency, right? If your detector looked at 100 speckles, they integrate, they cancel each other. You don't get good efficiency. So that sort of, there's a constraint there that kind of that's one constraint that designs how that influences your design for how you set up the field of view of the receiver. The other constraint is how many pixels are in the array, 640 by 512, and another constraint is, another thing to consider is the fringe spacing. Like when you want to set up the fringes so that your pupil, this by the way is an image of the pupil of the receiver. And we've got some, because it's just a Fourier transform of the image data. And if Joe has some data where he used telescopes that have a secondary that blocks it, and so we get like a donut pupil, just like you'd expect. So you want to set up the spatial fringe pattern, the angle between the LO and the reference. Actually, we get by with half of what Joe calls the holographic condition, which you guys probably all know. It's kind of new to me. The holographic condition, I think, separates this guy from the autocorrelation term that's here. We don't need that in coherent detection because this guy's amplified by the LO. So yes, there's interference there, but we don't need that much separation. As long as we can get away from the local oscillator tremendous spike at DC, we're probably doing pretty well. So all those things, when you think about the details of it, they go into essentially, I think, the part of the answer to your question, which was what's defining or limiting the field of view. The other thing that really does it, in my opinion, is the transmitter. If I want to expose your face at 100 meters versus 50 people's faces at 100 meters, I'm going to need 50 times the transmit power to do the second job. So generally speaking, you can't. LiDAR and wide field of view imaging are not compatible. All right?
Thank you again
Okay.
for